Hey, good morning, team. Chemistry coach coming at you with some more thermochemistry. Yay! All right, you either love it or hate it. And pretty much you're like, where's the negative sign go? And then you're good with thermochemistry, right? Define your standard states and reference states and all this fun stuff. Um, we're going to get into the meat of that today. Are you ready? So we were pretty much one of the focuses of this chapter is to calculate heats of reaction, right? The delta H values. And we looked at experimentally how to do that with coffee cup calorimeters, bomb calorimeters. We looked at that as an estimate using bond energies theoretically, see if it's exo or endothermic. But we're going to get into some more, accurate ways of determining delta H reactions theoretically. So I listed these off before when we talked, if you look at the video of determining heats of reaction. The two ways we have left is Hess's law, which we'll do in the next video, and then using standard enthalpies of formation. So we can get standard heats of reaction using standard enthalpies of formation. Again, if we're at constant pressure, enthalpy, heat are used interchangeably, right? Because the enthalpy change is the heat, right, at constant pressure. So you'll see those used interchangeably, and you'll hear me say, standard heats of reaction, when really it should be standard enthalpies of reaction. So a couple terms we need to nail down here. What am I talking about when I mean standard? We haven't really looked at that yet. What do you mean standard? I think we know formation, right? We're forming something. So before we can determine the heats of reaction at what I'm going to define as standard states in a little bit, we have to define enthalpies of formation. If we're going to use those to determine heats of reaction, we got to, define what these are. So you ready? The enthalpy change, and you'll see different definitions of this. So it's a standard enthalpy of formation is the enthalpy change. Remember, we can't determine, an individual enthalpy. We can only determine the changes between this state and this state, right? We can determine those. So it's the change that occurs when we're forming, by definition, exactly 1 mole. So that's going to make our coefficients a little weird when we do some equations on the next board. So we're going to take 1 mole of any substance and form it, right? What's the enthalpy change that happens? From what? From the elements, from its elements, the reference forms of those elements. Ew, what's that? At their standard states. Ooh, what's that? Oh my God, so many definitions. And to make it worse, it's temperature dependent. So we're gonna look more at temperature dependency in second semester general chemistry. So a lot of this particular semester, we're just going to define a temperature. We'll get tables of this at 25 degrees Celsius, or 298.15 Kelvin. Or we'll make simplifying assumptions that it's temperature dependent at the range we're at, just to make life simple. But we'll look more quantitatively at how it is dependent on temperature next semester if you take it. So what I want to do is define, what do I mean by reference forms of the elements? And what do I mean by standard states? But you can see the notation for the standard enthalpy of formation. That delta, it's the change, right? The change. So if I'm here, if I have its elements in the reference states, right, and at the standard states, and then the substance is here, that change is the delta H. The sub F is the formation, right? So when you see that little subscript F, that means it's a standard enthalpy of formation. And that little, degree symbol or not sign, that's what the standard means. So standard, is that little degree or not symbol. Whenever you see it, that means we are at these defined standard states. So let's do that on the next board. Let's do, what are these reference forms? I'm talking about the elements. And what are standard states? And then we'll look at some equations that kind of show us what this is all about. So we're going to take a whole video just to define all this garbage, right? And then in the next video, we'll take these values, these standard enthalpies of formation, and calculate standard heats of reaction. All right, let's get on to the next board. All right, let's take a look at these two defined things we're using here, like lots of defined states. We'll see this very commonly if you go to second semester general chemistry, more so than we do now. A lot of times we need a reference state, especially when we do it mathematically. We need this defined zero state, right? We're like, okay, we're going to define this at zero, kind of like with atomic masses. We define the carbon-12 isotope as 12 atomic mass units and get all the other ones relative to that one. We always need these reference states, right? So we're all speaking the same language. So when I say reference form of an element, right? So standard enthalpies of formation, we're forming some substance from its elements, the reference form of those elements in their standard states. We'll do standard states next. So what do I mean by reference form of an element? The most stable form of that element at the given temperature. And 999 out of 1,000 times at this level, we're going to be around room temperature, okay? So you can just look at a lot of periodic tables. They shade them different colors. But hopefully by now you're fairly familiar with the most stable states of the elements roughly at room temperature and at a pressure of 1 bar. Used to be, it was 1 atmosphere forever, but several decades ago, the International Union of Pure and Applied Chemistry said, no, we want it to be 1 bar. Why did you change it? But they're so close to each other. What is like 1.01325 bar per it's really, really close to each other. So a lot of tables we use are at 1 atmosphere still. Technically, it should be 1 bar, but the difference in the values is so minute that the details of calculations we're going to do now, there probably wouldn't be that big of a difference noticeably in our final rounded value. So I'm okay at this level at 1 atmosphere or 1 bar pressure. So what would that mean? Okay, well, we know nitrogen gas is diatomic, right? And a gas. The element nitrogen is a gas and diatomic at those conditions. Bromine is a liquid, right? Where hydrogen's a gas, oxygen's a gas, all those, you should know those states. Carbon is a tricky one because it has different allotropes, right? We're familiar with diamond, things like that. But it turns out the most stable form is graphite, right? So thermodynamically over time, diamond actually converts into graphite, but it takes a long time. That's called kinetics. We'll learn that next semester. Of course, most of the metals are going to be solids, except I think mercury is a liquid. I think you're all pretty comfortable with that. So when we say reference form, that's what I'm talking about, the most stable form at roughly 1 atmosphere or exactly 1 bar pressure. Let's look at standard states next. I'll write those up for you. You guys ready for some standard states? We're going to hit these really heavy in second semester general chemistry, all right? But whenever we say standard states or conditions, right, it's a defined set of conditions you're going to see these species at. And these could be for elements, molecules, ions. It doesn't matter what those species are. Right? But we're going to need this when we're defining standard enthalpies of formation. So we're forming exactly 1 mole of the substance at its standard states or set of conditions from its elements and their reference forms under standard states or conditions. So here's these defined set of conditions. Useful for when we're tabulating values, right? It's the pure species. No duh, right? Pressure, again, 1 bar, which is approximately 1 atmosphere. We're going to use those interchangeably in the first semester. If it's a gas, we're going to consider it an ideal gas. Yay! All right. Can be at any temperature, whatever the defined temperature is, but tables, tabulated values of this, my gosh, we can't have them at every single temperature. So very commonly, you'll see tables in the back of your book with these standard enthalpies of formation at 25 degrees Celsius as a temperature. So 25.0 typically, 298.15 Kelvin. If it's a solution, not a big a deal at first semester general chemistry, but in second semester general chemistry, we're going to make more of a fuss over this. For solutions, the concentration will have what's called an activity of 1. Hey, what's activity? We'll find out next semester, okay? So for now, we'll just call that 1 molar, right? And we're going to find out in a little bit. We define an ion as 0, our 0 state. That's the hydrogen ion for that. Okay, so now that we have our definitions, let's look at some reactions for these standard enthalpies of formation. Yay! If you're feeling daring, right, you can attempt these yourself. So let's look at some standard enthalpies of formation. Remember, we got that little degree or not symbol, standard conditions. Enthalpies of formation, the little sub F. Here's some equations. Now, we're going to see in the back of the book, they just give us the value for that. They don't show us the equations, but if you ever need to write the equation, this is how you go about it. Now, remember, the trick to this is we're, by definition, forming exactly 1 mole of this substance, which means we may end up with some fractional coefficients. I've told you at this point to avoid fractions as coefficients, but for now, with thermodynamics, by definition, if we're forming exactly 1 mole of something, we may need to use fractions, possibly. Oh no, fractions! So let's show you with the first one, and then if you want to pause it and try the other two, have at it. So in this case, we want to form 1 mole of water in the gas phase. The state is critical, gas, liquid, solid, AQ, because those will have different thermodynamic values. So I've been beating on you guys with an ugly stick to show your states, right, in your equations. You got to get into the habit of doing that. So, well, this consists of hydrogen and oxygen. All right, so for the reference form of that element at standard states, hydrogen at 1 bar pressure, roughly 1 atmosphere, is a gas, and it's diatomic, right? So this would be H2 gas. Oxygen is a gas, right? Typically, I didn't define temperature here, so we'll just assume roughly room temperature. It's a diatomic gas, right? We'll write down the forms, then we'll get the coefficients last, right? So we need to form exactly 1 mole. So we have to have a 1 here. Oh no! We have to have a 1. So when we put in the coefficients, right, the hydrogens are balanced, right? So we got 2 hydrogens, so we're good to go, but the oxygens are not. I have to have 1 oxygen on the right-hand side, which means I need a 1/2 mole of O2 there. Say the fractional coefficients? No! It's okay, my friends. So that's the equation for the formation of exactly 1 mole of water vapor. These are the pure elements, 1 bar pressure, whatever the defined temperature is, at their standard states. Right on? They're reference forms of that, the most stable state. So if you're daring, go ahead and pause it and try these next 2. You ready? So let's do this one. So we're forming 1 mole of this species. Carbon, remember the reference form for that. We talked about it. The most stable state, the reference form was not diamond, it was graphite. So we're going to take C as graphite. Usually we do that, or diamond or whatever. So this is the most stable form of it. And graphite is a solid. And then we're going to react it. So nitrogen. So that's diatomic, and it's a gas. All right, that's its stable form. So we're going to go into gas, forming C2N2. Gas at some temperature, and we're just assuming room temperature here. 1 bar pressure. That's an ugly looking parentheses. Now my finger's all brown. Cover up my black widow white. Is that balanced? Well, the nitrogens are, but the carbons are not, right? So I need 2, because for 1 mole, I need 2 nitrogens, 2 carbons. I got 2 nitrogens, so I need to put a 2 in front of the graphite. Not too tough, right? Oh, my color coding is off. I must stay consistent. My coefficients in red. Not that it matters. This one's a little trickier. I saved the toughest one for last. And then what we'll do is we'll look up these values, right? There's tables in the back of your book. For us, it's Appendix D. So here we go. So we're forming sodium nitrate solid. So that's going to be formed. We got 3 elements this time. So sodium is a solid, right? That's its stable form in its reference state. And it's monatomic, correct? So this would be Na solid. Nitrogen we've already done. That's a diatomic gas. Oxygen is a diatomic gas. And we're forming exactly 1 mole of NaNO3. So now, let me get my red pen. These sodiums are balanced. Yay, we've got 1 of each. We have 2 nitrogens and 1, but we have to have 1 on the right-hand side, correct? Which means we have to put a 1/2 in front of the nitrogen in order to get 1 mole on that side. We've got 3 here, so in order to get 3 here, we had to have to multiply the diatomic oxygen by 3/2, right? 3/2 times 2 is 3. Boom! So there we have 1. This is, now the enthalpy change that occurs under standard conditions for these specific reactions, whatever that value is, right? It could be exothermic, negative. It could be endothermic, positive, whatever it is. Those are tabulated, all right? So I'm going to make a note of that. Let me pause it. I'm going to write up some information on the tabulations, and I'm going to go grab a table. If you have your textbook, turn towards the end. Look for appendix. For ours, it's appendix D. Usually it's one of the, depending what textbook you have. It's in one of the appendices. And you'll probably see these thermodynamic tables that have these standard enthalpies of formation, but you'll typically have that along with a couple other tables, columns that we're going to use for next semester with entropy values and Gibbs energy or Gibbs free energy values. We're only focused on the enthalpy of formation value, which usually is the first column, not always. So see if you can find that real quick, and I'm going to write up this information on the board for you. Did you find your appendix D? All right. Now those, a lot of times, at least for my class, I type up all those appendices and tables, but that's a really long one. So what I did, when I do exams, I just type up enough to fit on 2 pages, right? So you'll see something like this, where it's broken up by elements, for example, oxygen, and then you'll see the different types of oxygen in their states, and then here's your standard enthalpy of formation. We'll be using Gibbs energy and entropies next semester. So we're only focused on this orange one, this first column. These are all in kilojoules per mole, right? So you just find the element, right, alphabetically, and find whichever, species you're looking for, and just look over and find the value. Hey, these are not exact values unless they're defined, right? The values for 0 are defined there. So for water, we would look up, we don't know if it's under hydrogen or oxygen, right? So it's obviously not under oxygen. So we have to find hydrogen, right? So here's our hydrogen. So you scroll down until you find water. So there's water as a gas and water as a liquid, right? And this is a gas this time. So we have to find that value, the negative 241.8, right? And kilojoules per mole. Right? By definition, it's 1 mole. And that would have the 4 significant digits. They're different tables, they may go out more decimals or less decimals, whatever it is. Just use whatever provided in the table or whatever's provided for you on an exam. And this is not a complete table, so if it's not on here, I would have to give you that value. I don't expect you to memorize these. I'd give you that value on an exam or quiz or something. Let's look up C2N2. Now, we don't know if it's under carbon or nitrogen, so I've got nitrogen here. It doesn't look like it's in there, so it's probably under carbon. Here's carbon. All right, I've scribbled all over my table, right? This, I just typed up a few of them. So C2N2, there it is right there, C2N2 gas. And there's your value, 309.0. Now notice this one is positive, it's endothermic. This one is negative, it's exothermic. Whoa, so we can have different values, could even be 0. If it's an element, notice elements, right? So like hydrogen gas is 0. Right? I talked about the H plus ion in solution being defined as 0. Right? So anytime you see an element in its standard state, the reference form of it, it's going to be 0. Because you're forming 1 mole of that element as a reference state, as standard states, from its most stable element reference state into standard states. You're forming what you're starting with. Oh, that would be 0, right? So all those elements are zeros. You don't have to look them up. You're just like, hey, H2 gas, 0. O2 gas, 0. N2 gas, 0. Copper solid, 0. Graphite, 0. Right? So if we look under carbon, you'll see there's your graphite, which is 0, but diamond is not. Ha ha ha. Pretty close. So in this scenario, water would be more favorable, right? The hydrogen and oxygen would rather be water, right? So they have a tendency to form water. So if the 0 states here, this would be the hydrogen, say we have a level here. If we did like an enthalpy diagram, the hydrogen and oxygen, half a mole of oxygen gas, 1 mole of hydrogen gas, if that's 0 here, the water would be, boop, down here at negative 241.8. So it drops, okay? So we would call that more favorable. So forming water vapor would be favorable. Whereas the C2N2, that's not as favorable. It'd rather stay as its elements. So if we had 2 moles of graphite and 1 mole of nitrogen gas here at the 0 state, the 1 mole of C2N2 gas would be up here, way up here at 309.0 kilojoules per mole. So not a favorable process. Doesn't mean that can't exist. Just means this probably is a little more reactive, right, than water vapor in that scenario. Give or take. And then for sodium nitrate, that one, I don't have that on the table. I couldn't get everything on 2 pages, so that's not on here. But if you look in your appendix, you'll find negative 467.9 kilojoules per mole. And you could write it as kilojoules over mole or kilojoules times mole to the -1, right? I ran out of space there, so that's nice to have that. So that's really favorable, right? So it's 1 mole of sodium solid, half a mole of nitrogen gas, 3/2 moles of oxygen gas at the zero states here. 1 mole of sodium nitrate's way off the chart down in the dungeon. All right, negative 467.9. So they'd much rather be in that ionic compound right there. Hey! So now that you see those values and you can find them in Appendix D, I will give you something like this on exams. This is posted on my particular website as well. And again, it's not a complete list. That's just what I could cram on one page double-sided. Right? So I'll use those for exams. We are now, and again, these are tabulated specifically at 25 degrees Celsius, which is 298.15 Kelvin exactly. So if we're at that temperature, we can use this table. If we're not at that temperature, we got a problem, right? We'll talk about how to adjust for that next semester. So for this class, to use these values, I'm going to have to do the equations at 25 degrees Celsius. Unless I make the approximate statement that treat it as temperature independent, which it isn't. But if we want to do it at a different temperature and use these values, we're going to have to make that assumption for first semester of general chemistry, right? We'll do the quantitative adjustments next semester. Ooh, not necessarily as fun. So what we want to do in the next video, now that we know what standard enthalpies of formation are, we want to use these to calculate standard heats of reaction, right? So we've got a reaction that occurs, right? At some temperature, we would have to be at 25 degrees Celsius in order to use these values from Appendix D. And so let's talk about how we can use these standard heats of formation to calculate standard heats of reaction. Remember, standard conditions, 1 bar pressure, yada, 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 pure forms of those elements, ideal gases. Let's do it. All right.